Hello. How you doing? Good. Hey, man. Right. I think we'll probably get going just because it's 5 o'clock and there's quite a few questions to get through. Just as a prior warning, I'm not going to do question 4. The reason I'm not going to do question 4 is they're going to release a video on it that's way more in depth than the explanation that I could probably give you. So just wait for that video. Yes?
There's no lights here?
Yes. That's because the board was crap, but we can put lights on, potentially, somewhere. One of these buttons will produce light. Or maybe not. 2 seconds. Did that do it?
Yeah, it's better.
Cool. Right, yeah. So, yeah, question 4, I'm not going to do. Reason being that they're going to release a better version than I can do online because it's quite involved. And I didn't get time to fully run through the solution because I had my first year Viva today. So I'm running on the example sheet today, so not as many notes as usual. But I've had a look through and I do get these questions. And actually, question 6 was on my exam paper, which is quite funny. So we'll start on question 1. We're asked to find this. So we've got this kind of U-bend tube, and it's rotating around this axis here, which we'll call the origin. And it's doing so with it's doing so with an angular speed of omega, right? The notation he uses in the book is this, but this is more correct. Well, for this case it is anyway. And the water up the side, on this side is going up about 20 centimeters, and this one's going up 12 centimeters, right? And this one's 5 centimeters. This 12 centimeter is 5 centimeters from the axis of rotation, and this one is 10 centimeters from the axis of rotation. And in a bit more detail, you can see we've kind of got this slope. Do you remember when we had that tank accelerating to the right before, and it created that kind of slope fluid? It's a similar thing. In angular motion, the thing is technically always accelerating linearly, but that's another story. And we're asked to find what this is so that these two fluids will balance to this particular configuration. So there's only one angular speed that will do this. The first thing to realize, and apparently according to one of the more competent GTAs, this is proved in, so this one I'm going to write comes from equation 2.43 in your book, which you've got page 85, okay? And that proves what I'm about to just pull out of my arse, and that is that the pressure, the change in pressure with the radius is equal to the density times the velocity over r, okay? So this is essentially saying that as we move away from this axis of rotation, this is how the velocity varies. I'm not going to explain it, but look it up in the book, just for the sake of moving on. In order to convert angular speed to, convert linear velocity into angular velocity, we can write rho omega r. Oh, sorry, that's squared, right? Because that comes from u equals omega r. Okay? Are we happy with that? So we've got this equation here, and this relates our change in pressure with the change in radius to the angular velocity. So even though the arms are on different sides of the rotational axis, they are essentially just sitting at 2 different radii. So, I mean, you could like twist them the same way. It wouldn't matter where you put them, really. They will always balance like that. And there's no vertical motion as well. So the pressure is hydrostatic, okay? So that means that we can integrate this equation in order to get, I'm just going to zoom this out a little bit. Hopefully it doesn't detriment the viewing too much. Is that okay? Can we still see that? Hang on, let me put the autofocus on and it might do nothing. Right, so I'm just going to integrate this equation. So when we integrate this, that essentially means we have dP equals rho omega squared r dr. And I'm going to write them as definitive differentials, even though it doesn't really matter for your level of maths, but it just makes it clearer for me. P2. So this comes out as P, right? With between the bounds P2, yeah, and P1, right? Where I think, let me just double check that I've got this the correct way round. That. Oh, it's irrelevant which way round you pick it, because it's going to go away at the end of the day anyway, okay? So P2 and P1 can be whatever you want. Assume they're just P2 and P1. It doesn't matter which ones you label them as. Just checking I've got that right. Yep, okay. So that's between those two. So if you've not got any variable there, you treat it as a constant, and the integral of 1 just becomes the variable. Are we happy with what I've done there? Right? And then this part of the equation will end up being this. Okay? Because we've just put in these P2, P1s, right? P2 being one of these, P1 being one of these. It doesn't really matter which way around they go. And then doing this side of the equation, we can take this out as a constant, and we've got r here. Yep, we've got r here. So that's going to go to r squared over 2, right? And then that's between r2 and r1. Ooh, it may make a difference. Will it? Let's say P2 is the bigger one, just for the sake of argument. It's not stated here, but I think that's probably the best way to do it. Biggest minus smallest, okay? So this one here, this will be 2, and this will be 1, okay? And if the math doesn't work out, it's the other way around. What do we write? What has he written there? Oh, the depth, right. So this balance in pressure, let me just finish off writing this out. R2 minus R2 squared minus R1 squared. Okay. This balance in pressure is equal to the columns here, the pressure of the columns here. Okay. So we can write our hydrostatics equation, which is rho g d2 minus d1. Okay. So we just basically balanced the pressures in here with the pressures in here. Hello. Yeah, pressures in these tubes here are balanced with these tubes here. So all we really need to do now is isolate omega in this equation here, because that's what we're looking for. Oops, sorry. So just isolate that. When you mess around with the maths, do you want me to mess around with the maths, or are you guys all right doing this yourself, do you reckon? Just isolating this omega from these two terms? You think you're okay with that? I'll just write it out. If anyone is confused about where anything comes from here, just shout out. Or don't shout out, put your hand up like a respectful human being. D2 minus D1 over R squared 2 minus R squared 1. Right? So when we put in the numbers for this, so D will be, this is depth 2 and depth 1, and this is R2 and R1. When you put them in, you end up with 14.5 rads a second, which if you then convert to revolutions per second, gives you 138 revolutions per second. Okay? And that's the answer to that equation. Is everyone okay with that one? Does everyone understand what we've done? Yeah, what's up?
How did you get 2y?
What, sorry?
2y. How did you get it?
Where are you looking?
Down the last
This is a G.
What's the G?
It's a gravitational constant. Comes from here. Where did 2 come from?
Yeah.
Not sure. Oh, here. There. Comes from the little bottom there. Happy?
Yeah.
Cool. Okay. Where'd it go? Oh, there it is. So, the next question is a buoyancy question. Ooh, buoyancies. Ooh, yeah. Okay. Question 2. It's all balanced. It's all equilibrium. So we've got a block of steel with specific gravity of 7.85, a heavy boy. And it's floating, in quotes I've written on the sheet. I always like when they do that. We got, hang on a sec. We got water, and we have mercury. Right? And it's there's a ratio of the depths that the block sits in both, A, B. and we're asked to find this ratio between the distance. So we want to know A over B. Okay? So we're going to do this by using, by understanding that the weight of the block, the downward weight of the block, is balanced by the buoyancy forces. Okay? And they act all over the place. So the first thing we want to do is probably find the weight of the block. So I'm going to write area is equal to A. We'll just have a value because we're not actually given dimensions of the box. And I'm going to write that the weight is equal to the density of the steel times the gravitational constant times the steel block's volume. Okay, we happy with that? And I'm going to call area. If you imagine the box is, can you guys see that? Okay. If it slips off the screen, do shout because I'm not always looking. If we've got this box like this in 3 dimensions, expanding to the 3rd dimension, this will be A plus B, right? That there, and this will be A. Okay, so that's where the buoyancy force acts on these areas here, and A plus B is this here. Okay, so all I've done is taken that and just showed you it. Okay, so if we want the volume of the box, this is going to be equal to, well, first off, the density of steel can be calculated from the specific gravity, which is rho W SG. So that's just a thing you've seen a million times. Oops, not equals. Sorry, I can't rub it out. Oh, pen. And then the volume here, there's a G. The volume here is equal to A plus B times by the area. Okay, and that's our weight force. Are we happy where I got that? Yeah. Yeah. Cool.
Which formula is this?
This formula. This is the weight. This is just the weight of the box.
Oh.
Yeah. Think about what it's saying. It's saying that the density of the steel times the volume, i.e. its mass, times G. Right? It's the weight. Yeah. If you're ever in doubt about what formula is saying, just think about the units of the variables. Okay. If you can write out dimensional analysis, you'll see that this summarizes to the units of newtons, and therefore you can understand that it's a weight. Okay. That's kind of usually where most formulas are built from anyway, is trying to balance the dimensions. So, I mean, this has got units of meters cubed. This is meters cubed, kilograms per meters cubed, right? And G is what meters per second. So it'll balance out at, of course, newtons. I can't, what's the thing of newtons? Whatever. It will do that. So next we're going to calculate the buoyancy forces. So we've got, spelling buoyancy is a weird one. Is equal to I'm going to put water, and I'm going to I'm going to do buoyancy of the water plus the buoyancy of the mercury. Okay, so that's just our buoyancy force acting on this bad boy. Yeah. Okay. So the buoyancy force is equal to the rho of the water times the bit that's submerged in water times the area that it's acting on times G. Okay? Because if you think about it, the water's resisting the weight of the block in a way, and it's just the amount that's submerged under the block. So this is again our volume. This is a volume. Yeah? So the water's only acting on the bit that's in water. And then we've got the extra bit, which is rho Hg. Oops, I don't know what's going on there. Rho Hg, and then this bit's only acting on BAg. Okay? And if we write this lovely equation out and rearrange it, we end up with alright. So it's rho W Ag, so that comes out of both. And then we've got A plus B, and the B is times by the specific gravity of Mercury. Does anyone remember what that is? Off the top of your head?
Something 13 something, yeah?
Yeah, it's 13.56, so you weren't far off, yeah. So, yeah, when we rewrite that, it comes out at rho W A G A plus 13.56 B. Okay? And now all it is a case of equating the two forces, because the thing's floating. Okay? So the weight is balanced by those buoyancy forces. Just classic Newton. It's coming at you again. So we write 7. I didn't specifically say that. Oh yeah, yeah. We're just filling in the numbers. This is the specific gravity of steel. Okay, so 7.85 rho wg a plus b equals to the buoyancy forces, which is rho w ag a plus 13.56 b. Okay, and then all we're going to do is we're going to cancel this out. Bang, bang. We're going to cancel this out. Bang, bang. We're going to cancel this and this. Did anyone here do foundation year? Did you have Borovic for logic? Oh, that's a shame. Borovic was this like Russian dude, and he used to, when he cancelled things out, he'd be like, "Kill it!" It's so funny. I always used to see him on the bus. It was great. Anyway, what you end up with, oh, he's a good dude. What you end up with is this when you rearrange it, right? So all I'm doing, I've cancelled everything out but the numbers in A and B, which are the bits we wanted to find. And when you rearrange it and do all the numbers, the necessary calculations, you end up with this. And then you can rearrange that to say A over B is equal to, I think that comes out at 834. Yeah? We happy with that? Just to recap, basically this block's floating in these waters, submerged a bit in water and mercury. It's submerged a bit in water and it's submerged a little bit in mercury. We said that the weight was equal to rho g volume, because it is, and then we said that that's A plus B A because it describes the volume of the block. Okay? And then we equated that to the buoyancy forces, which we said are the buoyancy of the bit balanced in water and the buoyancy of the bit balanced in mercury. And we said that the bit balanced in water was the density of the water times the volume of the block that's submerged in water times g, and then the same for mercury. And then what we did was just equated the two and solved for A over B. Happy? Yes?
Is that 56?
Where are you looking? There?
Up?
There? Yes, 13.56.
Above it?
Above that, 13.56.
Above that?
Above that, SG. Specific gravity. Cool. Ooh, these pages are stuck together. That's quite surprising. What a nice surprise. Okay. Ooh, question 3. Ooh, fun. Okay. Okay, so we've got for question 3, we've got a jet of water. Well, blam, there's the jet. Wowzers. Look at it go. And it's got some variables associated with it, which are its volume, its volume flow rate, and its density. And what it's doing is hitting this big old plate. And that's a plate. Okay? And the plate's inclined at an angle, theta. And what we've got here is a fraction, a bit of the volume flow rate. This is a fraction. Okay? So rational. And a bit of and some volume there. And here we've got 1 minus that fraction times q and the volume, right? Basically the flow's splitting in half. And we're told that there's no viscous effects. So that means that any effect tangentially, Ft, some force resisting that motion as it moves across the plate, is removed. So there's nothing, okay? So Ft equals 0. That's basically saying there's no friction on the plate. It's an amazing plate, and I don't know why we're not using it to build a heat engine, a perpetual motion machine. Let me just read the question a little bit more, it's quite a long one. No tangential force. Under this condition, find that fraction as a function of the plate angle, okay? Also find the normal force, i.e. This force, Fn, exerted by the plate on the fluid. And the density of the fluid may be assumed to remain constant. So we're dealing with an incompressible fluid. So, first step, find alpha. So we want alpha, that's a question mark. We want Fn, that's also a question mark. Okay? Find alpha, we consider the yes, I'll remember now. Yes? Yes. Okay, so we're going to do a momentum balance first off. Okay? So the first little bit of the momentum balance is we're going to write the force tangential to the plane, the bit that will try and change that momentum, is equal to 0. Okay? That's the first bit. We said that earlier. It's given by that shear condition. And then what we're going to do we've got alpha rho q v. So this is the mass of the fluid going this way. No, this way. And we've got 1 minus alpha. And remember that velocity in theory shouldn't change. This isn't volume, this is velocity. Sorry, I got confused because I used the v, not a u. There we go. That's much better. I think it's velocity anyway. Well, I'd say it's velocity. We're doing momentum. Mass times volume.
Is it bracket or P?
What are you looking for?
Yeah,
What, there?
the first one before.
That?
Yeah.
As a bracket. Yeah. So the velocity won't change when it hits the plate because there's nothing changing it, right? That's essentially what we're writing here. The momentum remains constant. The only thing that splits is the mass. Right. Yes. That's where we are. Q, and then I'm using U's now for velocity because it's more consistent with fluid dynamics. Right. Cos theta, moving through the angle. Yeah. Okay. So because we're dealing with the tangential force, yeah. What's up?
What's Q?
The volume flow rate. Okay. So how much fluid is flowing through a little volume at one time? Okay. Yeah. Because we're dealing with the tangential force on this plate that's angled at a cosine theta. If we want to figure out the momentum contribution here, we need to. It's going to be a minus. It's going to be rho q, and then that velocity. But we've got to add that cos theta factor, okay? Because we're rotating we're essentially taking the component of the force that acts in that tangential plane, right? So this bit here, what of that is acting here? The momentum, right? Happy with that? Does everyone understand what I've done? Yeah? Yeses are also acceptable. You can say yes. It very much helps more than silence, to be honest. Okay, and then what we're going to do, because remember we don't know theta. We don't know theta. We don't know. We're just writing an expression for that fraction in terms of theta. So we can rearrange this equation into 2 alpha equals 1 plus cos theta, which is nice and sexy, nice and easy, right? And then if we rearrange this, we end up at 1 plus cos theta over 2 is equal. Oh, I've written cos theta cos alpha. That's because in my PhD the actuators have alpha as their thing, so I'm so used to writing it that my brain just did it. That's wacky. There we go. Okay, so let me just double check. I can tell you what we did there. 1 plus cos, yeah, fine. Yeah, so if you played around with this and just sort of moved everything over the brackets and stuff and cancelled things out, you would end up with this, okay? Does anyone need to see that, or are you pretty confident you could do that on your own? It's essentially just algebra, right? Just moving things over the equal sign. Because we've got a 0 here, which means that any term can be, any term that's on its, like any of these terms can really be moved over each side at will, and you can cancel things as you go, okay? Are we happy with what I've done there? Excellent. So now we need to find the normal, the force in the normal direction to the plane. So this is also nothing, apparently. Okay. So we've got to find the. Yeah. Do I get that? I get that. Do I? Oh yeah. Okay. Yeah. So it's going to be, these aren't going to contribute at all to the normal force, okay? Because they're just rolling on their merry way down the plate. But this does contribute to the normal force because this plate has to resist this impact, okay? So we can write that as rho q, and it's going to be minus the velocity this time because it's going the other way to resist these things, and that's sorry, this is in brackets because it's not minusing. It's part of the term. So this is basically saying that the force in the normal direction is equal to no contribution from those jets going off this way, and the contribution from this coming in. All right, are we happy with that? And I've rotated by sine theta to make it get me the normal component. Right? Okay. And when you rearrange this, it ends up like this. because there's not really much rearranging to do. Okay? So these are your answers in that case. Is anyone happy with what I've done? Do we need a recap? Recap might be useful, maybe? Yeah. So we're given this question, jet of water coming on the plate, right? Splitting in two. That means, and it's doing so with no friction from the plate. This essentially means that we can say that the tangential force is equal to 0. We're asked to find a function that relates the angle here, theta, to the fraction in alpha that divides the stream. Okay. So the way we did that was we considered the moment tangential to the plane. Ooh, that's fun. And we did that by making a momentum balance. Okay. So if there's no change in momentum, hang on. If there's no, fuck. Yeah. Oh, right. Wait. What's that doing? Fraction volume flow rate, kilograms per times velocity. That is momentum. So why is it equal to 0 mean? That's the same. Ah, yeah. So if there was a force tangential to the plane, that momentum would change as it moved along the plane, right? But because there is no force along that tangential plane, the momentum doesn't change. So therefore, we can equate this whole thing to 0 because this is the only change, right? These balance. Do we understand what that like? So this is these two, the tangential stuff, and this is the jet, right? So basically, all I'm saying is that these two would have to balance if there was no change in force. Okay? Are we happy?
Kind of.
Force is a change of momentum. Okay? So if there's no change in momentum, it means the momentum's in equilibrium, right? And that's essentially what we've written here. If you were to move this onto the other side, it would, like this jet momentum term, it would say that the momentum of the jet is equal to the momentum of the two ones going to the tangential directions. Okay, that we've just all preemptively moved it. Okay, it's kind of like a moment's balance. The two are in equilibrium because there's no change in momentum because there's no force. Okay, and then because the fractions involved in both of these, we can just move these things about on the equal sign and cancel things out to get this. Yeah, so
Where do you get that alpha from?
that's given in the question. That's the fraction we're looking for. So that's the fraction in which the streams diverge. The fraction which splits the streams.
But there's no P.
Sorry?
There's no P.
What do you mean P? Do you mean rho?
Oh, is that a rho?
That's rho. These are rhos. If I'm drawing a P, it will look like this. If I'm drawing a rho, it will look like that. Okay? I know it's not entirely clear probably on your screen. It's a bit more curly and slanted when I write rows. They're not. I know it's not particularly. Yeah, it's difficult. Some people do rows really fancy, like they do like this, but nah. Yeah, and then essentially we just said that the normal force. There's no contribution to the normal force from this, but there is a contribution from this. So I just used the same principle in order to get this. Okay. Yeah.
Will we get similar questions in our exam?
You might do. I have no idea. I don't know your exam. I haven't seen it. You get some questions. You might get something like this. What you're going to get in your exam is essentially questions that are going to just make sure you have an understanding, probably of mass conservation, probably of buoyancy, probably stuff like conservation of momentum, conservation of mass, stuff like some hydrostatic equations. You'll probably get. You remember we did that whole tutorial that was basically hydrostatics and like different heights of things in manometers. You'll probably get something like that. You'll probably also get like one really big question that involves doing a bunch of little things that you've already done in order to create a big answer. Right? If you see a big question and you're like, oh my god, that's a huge question, how am I going to do it? Most of the time it's stuff you know, just like you have to do a lot of them at once, right? So just start throwing numbers at the wall. If you're ever stuck, conservation of mass, conservation of momentum are usually your go-tos, okay? And then hydrostatics on top of that. If something's in motion, the force isn't going to be balanced. If something's not in motion, it's in equilibrium, the forces are balanced, okay? There's no change in momentum. Yeah? So that's the sort of stuff you'll get in your exam. This tutorial sheet actually has one of my exam questions on it from when I did this exam, question 6, which was quite freaky to see. But yeah, you won't. if you revise hard, and like my tip for your revision in uni exams is just go through every tutorial again and just make sure you understand it all to like the max. Like follow the solutions through and just go, right, how did they do this? Right, how did they do this? How did they do this? And just go. And once you can explain the whole of all tutorials, you'll probably be okay for the exam. And do the same for the exam papers as well. Just like, if you've got like, I don't know, I can't remember if they still do it the way that they did it with me, but we used to have like a couple of days before the exam, right? I would do every single exam paper, and the way I do it was I would ramp up in the amount that I didn't see. So the first one I do, and I just follow the solution sheet through. And I'd be like, right, how do they do that? How do they do that? How do they do that? And then the next part, I would be like, right, I'm going to give it a go without the solution sheet, and then like critique my answers and say, okay, I did that wrong because I was thinking this, but this is the correct way to do it. And then you just keep doing blind tests. And then just use every resource available and just make sure you understand how to do it all, because they're not going to give you something that's not on these sheets, you know. Like there'll be different questions, but the methodologies will all be the same. Okay? So don't worry too much about what type of questions are coming up on the exam. If you understand the principles, you'll get it. Yeah.
Here, why did you fit the force to the momentum?
Oh yeah, good point. Why did I do that? What the fuck? I did it because it's on the sheet. 2 seconds, let me figure this out for you. What? Yeah, what the hell? Oh, right, yeah. No, wait. Hang on. I'm nearly there. I think the reason is because that would be the momentum component. So in this case, yeah, this one up here, we're saying that the change in momentum, force, is equal to 0. And this is the momentum component that acts tangentially to the plane, right? But where does the other bit of momentum go, right? It goes into the normal force, right? So this change in momentum is equal to that force, right? Because that's cancelled by the normal force.
So the momentum is a force.
Hold on.
The change in momentum.
Yeah, okay, so sorry, forgive me. This volume flow rate is not part of momentum, right? It's not part of the mass. Well, it is a bit, but not really. The units of this are meters cubed per second, right? The amount of volume given per second. The units of the density are kilograms per volume, right? So the volumes in those two cancel out, okay? So we've got kilograms and seconds from those two. This meters per second from the velocity makes it this, which is kilogram meters per second, which I'm fairly sure is newtons, right? So it is a force. Okay, I was wrong in saying that this is the momentum, right? These are the forces that would change the momentum. Okay.
So rho Q is the mass flow.
It's not the mass flow. It's the volumetric flow rate.
Oh, okay.
That's. I thought that this made it the mass, but it doesn't. So I think. Yeah, so it's a bit weird. So if you think about this, imagine this is containing like the volume term, right? Then this rho times the volume is your mass, right? But we've also got the second term in here. That's because it's meters cubed per second, right? And then the u is meters per second. So it's weird. It's like having the mass and the acceleration, but like blended into variables. Okay, so like if you were to draw a line through there, this would be the mass and this would be the acceleration. Okay, does that make sense to people? Are we okay with that? Like I said, if you're ever in doubt about what you're doing, do the dimensional analysis. That's what I did there because I was in doubt. This is the dimensions of density, dimensions of the volumetric flow rate, and the dimensions of velocity. And I confirmed that it's newtons, so it's a force. And then I was like, right, so it's not momentum then. Okay. So if you're ever in doubt, check the units, right? This is like, yeah. I don't really know how to explain that to you guys, like in a way that's intuitive.
So Q dot is basically like Q over time?
No, it'd be volume over time.
Volume, okay.
Yeah.
So it's the change in force, not the impulse.
No. So it's a force. It's not the change in force. It's the force.
Yes, but the thing in the brackets.
That's a force. These are all forces. Okay, so they're acting to produce the momentum. I think that's the way it is. Okay, because if you imagine, well, I mean, this has got to change direction, which means it's going to create a force anyway. So I guess that's the force that maintains the momentum. If you can think about it like that.
You can start with F equals ma and then like that's what you did. If you want to simplify it more, you start with F equals ma to each force, and then you like
Yeah, that's true. So
change
it's
the A for velocity times time, and
Yeah.
then you change the mass to density times volume.
Yeah.
And made the volumetric.
Volumetric flow rate's correct.
Yeah, volumetric flow rate. The
Yeah.
T's cancel out. It stays a force, but
Yeah.
with different variables.
Yeah, so you're right. Yeah. So if you want to see, let me try and do that. So F equals ma, right? A is equal to sort of. Well, I mean, it's equal to the change in velocity over the change in time, right? And then mass is equal to density times volume. If you do volume over dt, dv, which is not that now, it's that, then you get q here. All right, and this is just v, rho v. Does that make sense to everyone? Are we on the same page now? Yeah. Sorry to be confusing. I fucked up on that one. Put it that way. Yeah. Okay. Should we talk about a rocket? Should we talk about a rocket now? Right. Get off this question. Talk about a rocket. No, like I said, I'm not going to do question 4. Question 4 is going to be done on a video, and probably better than the time I have to do it. So I would highly recommend you sit and study that when it's released. I'm not sure when it will be released, but it will be released. I'll ask you next time we do a meeting, which will be next week, and I'll tell you if it's not been released, when it will be. Okay, so we've got a big boy rocket. Lovely, we like rockets. That's why we all became engineers, is that right? That's right. That's why I became an engineer, because I like rockets. So the mass of the rocket, with all the fuel and everything, is 1,000 kilograms. It's a really, really, really light rocket. It's got a nozzle. I'm going to draw the rocket. I'm going to draw it not like they do. I'm going to draw it like this. It's a racket. It's got a nozzle. There it is. Whee! Hello. There's a man in there. And it's moving with an acceleration. Is that the acceleration? Yes, it is. It's called alpha, but I don't know why it's called that, so I'll call it... Oh, because they're going to use area, that's right. We'll call it alpha z. That's the acceleration in the vertical. And we're told that it needs to have that to be 3 meters per second. The area of its nozzle is equal to 300 centimeters squared. Okay? And it's exhausting hot gas at atmospheric pressure. Okay. Interesting rocket. It has a density of 0.4 kilograms per meters cubed. What else are we told? Yeah. Calculate the required velocity of the exhaust gas. Okay? Right. So again, we're going to use the forces and equate the forces. So we've got the weight of the rocket going down, right? What? Oh, that's interesting. Why is it done like that? Sorry, 2 seconds. What the fuck? Aren't they going the other way? That is bizarre. Has anyone? I've just got to do a quick check on the calculator. Has anyone got a calculator I can borrow quickly? Yes. Can you? Whoa, this is bougie. Look at that. Whoa, this is a monster. This is not exam legal. This is contraband. Oh my god, I don't know what to do. 1,000, yeah, and then with the brackets, there they are. Wow, what a beast. Can I keep this? Where's delete? There it is. Okay, cool. And then enter, I assume. Oh, that doesn't make any sense at all. Why is that happening? Oh, no. Yes, I understand. Right. Sorry, that's okay. Thank you so much. Right. Okay. So we've got this rocket. It's got a weight. Blah blah blah, and it's moving this way. Right. It's accelerating by g down as well. Therefore, this is where I got confused. The force that the rocket's got from its thrust, I'll call it Ft, has to equal the mass times both of these accelerations. Okay. Because it's got to. If you think about it, it's got to counteract gravity while also adding an additional 3 meters per second. Okay, so we can write this equation here. Yeah.
Shouldn't the g be negative?
That's what I thought. Hence why I was confused. But no, because if you think about it, if you're going up and you're producing a force to go up, if you produce g force, you will just stay still, which is kind of what we're doing. Yeah. To produce a force of 3 meters per second upwards, you need to produce the force that would counteract gravity plus the extra bit, right? So all we've done is combine the two into the acceleration term. Yeah? And we know all these values. We know them all. We know everything in the universe about this rocket. And so we get 1, 2, 8, 10 newtons. Okay? Cool. So the flow out for the rocket by using the momentum equation. Why did he say the momentum equation? This is not the momentum. It's mass flow rate. Bastard. That dot is way off center. This dude needs to use low tech. God damn. Okay, so the flow from the force from the we'll call it the exit, right? Is equal to the mass flow rate. It's crucial that this is the mass flow rate, right? I couldn't see the dot, hence why I was confused. Out of the nozzle times the velocity that it leaves the nozzle, right? And again, this is it's because it's the rate of the mass flow rate that this becomes a force, right? If it was just a mass, it would be a momentum. But as we've all learned through our unified confusion, we've come through and learned that mass flow rate produces the force of a fluid. Okay, and again, yeah. So here we go. We can write this as rho a v. This is velocity. Oh, you bugger! It's not v. It's u. That's m dot, and then we've got u out. Okay, and we just rearrange. It's very easy. So we've got u squared equals rho a. No, it doesn't. It equals 1 over rho a. Equals the force of rho a. Okay? We've got, and then we can just square root that, pow. And this gives us the, if we put in this force as this force, because remember they've got to balance so that we can take off. The thrust has got to produce a force that allows us to take off, so therefore it's producing this force. Then, so this is, we can write this, let me write this. Fe equals Ft, okay? So the force of the fluid leaving the nozzle has to equal the force of the thrust that we want. So then we can write Ft, I mean it's E as well. And we just put in the numbers, so that just goes 1, 2, 8, 10 over 0.4, 0.03. And this equals 1033 meters a second. Okay, so that's how fast our fluid, the values we've been given, has to leave the nozzle. Okay, be happy with that kind of question? Pretty easy. Force balance, okay? Any questions? No's also work. I see shaking heads. Good. Right. What was I gonna say something. Oh yeah, just as a little bit of a side, when you get into years when you have to write reports, like big reports, yeah, try write. There's a program. It's called LaTeX, right? It's basically a coding language that's a typeset, and it lets you write beautiful maths equations. Your lecturers will thank you. They will thank you. They won't give you extra marks, but boy howdy will they thank you. It is the optimal way to write scientific reports. Okay, well let's give this one a go. I didn't do this one, but we'll give it a good go. How long we got? Oh, we got 4 minutes. Do you guys want to see 6 or do you want to finish early? Does anyone need to see 6? Yo,
I want to see.
you want to see 6? Well, all right. We'll compromise. If you wish to leave now, you may. If you don't want to see 6, because we're getting towards the end of the session anyway. But I am going to go through 6, and we'll just see how it goes. So I did this equation in my exam, and I seem to remember getting it right. So I don't. We'll see how we do, huh? It's another buoyancy. That's why I remember getting it right. 'Cause it's a buoyancy one. So we've got a balloon. It's filled with some air, and it's got a payload. Okay, and that payload also has a weight. So we got the weight contributed from the air, and we got the weight contributing from the payload. So first part would be to say that the buoyancy of the air balances the weight of the balloon. Okay, are we happy with that kind of concept? Yes, man.
So what does that say?
Where are you looking? Oh, yeah. So that's FB.
Oh,
Let me just zoom in a little bit for you. No, wrong way. There you go. FB. This is weight 1. That's weight 2. So buoyancy balances weight. So let's calculate some weights, right? So the first one we have is the weight of the balloon itself, right? So this here. And we're told that that's filled. Oh, sorry, my bad. Let me just recap a second. We're told that the balloon has to support a weight of 1,300 newtons. I launched into this question a little bit fast, right? So the balloon, that means weight 2 has to equal 1,300 newtons. We're given that in the question, okay? And we're told that the ambient air is the classic 20 degrees 1 atmo, and the air inside the balloon is at 70. So inside the balloon is 70 degrees, but the same pressure. Okay, so this is getting a little bit into thermodynamics territory. We're asked, the question we're trying to solve before I launch into it, like I did there, is what diameter of the balloon do we need to support that weight that we have to support, this 1,300 newtons? Okay, so we want D, and that's a question mark, not a 2. So everything's got a balance, naturally. So let's look at the first weight. So we've got rho. Rho what? G? What the fuck is that? Why did he put G? That's bizarre. What? Why the G then? That's throwing me off. I was going to use the thing of the air, but whatever. Why G? Why G? What is that? Fucking what?
Is it the weight? So we don't
No, it's not. It's the weight of the balloon. But I thought the weight of the balloon would have like the weight of the air in it. I guess he's just using G as a different notation to differentiate between the ambient air and the weight air in the balloon. Right? I'll use capital A. So capital A is inside the balloon. Little a is outside the balloon. And it's probably likely that we'll run into a reason why he used G at some point down the line of this question, in which case I'll look like a total idiot, but continue on nonetheless. So we've got rho of the density of the air inside of the balloon. That's times by the volume of the balloon, which is pi r cubed, 4 over 3 pi r cubed, G. Yeah? This is the mass, that's the acceleration. Okay? And we've got the weight of the load, it's over here. And we've got the buoyancy force is going to equal the weight of the fluid displaced by that balloon. Okay? I should have said that in the question about the block, but now you know. So I'm going to write that because it's important. So FB is equal to the weight of the fluid displaced by the balloon. Balloon's a fun word to say. It almost has like a onomatopoeia to it. Okay, so the weight displaced by the balloon is equal to rho of the air outside of the balloon, which is at a different temperature and therefore has a different density. That's some thermodynamics that you don't necessarily, you might know just intrinsically, but you're not really, I don't know why you're expected to know that here. And that's 4/3 pi, oh, that's bizarre, r cubed. Okay, are we happy with what I've done there? Yeah, pretty easy, pretty standard. So we're told that this payload plus the weight of the balloon, which is this rho a 4/3 pi r cubed g, is equal to the weight of the water displaced because of the buoyancy force, right? Cool. What's next? What's next? What's next? So we can do some funky rearranging. We'll bring this whole term over this side of the equation, and we'll factor out 4/3 pi r cubed because it's the same, and g, and that gives us rho a minus rho a. Okay, equals 1300. Okay. If we were to solve that, we're told we want to find r, so we need to do a little bit more rearranging. That just allowed us to separate out r. So we'll do rho a minus rho a g 3/4, and that pi is going to come down as well. So we've got pi down here somewhere. Yeah, that's right? Yeah. I think that's right. He's done it in terms of diameter, which is really annoying, but yeah, diameter's going to just equal 2 of this. And then we're going to have to cube root the whole thing. Okay, because r is cubed. And this will give us r. We need to find the densities. Does anyone know about the perfect gas law? You ever heard of that before? Oh my gosh. Hands. Anyone? Yes? Yeah, pretty much, yeah. But there's another version that relates pressure and density together. So that's this. Okay? Perfect gas law. So we can use that to find the densities because we've got the pressures of the two, and we've got the temperatures of the two airs being used here. Yeah, I'm not going to do that. You could do that quite easy. I mean, it's just simply filling in the box. The same is true of this. Hang on, let me just write that for clarity. That'd be A. Yeah. So these are our perfect gas laws. PGL. Brah. So the density of A ends up being 1.19 kilograms per meters to the minus 3, and the density of A, the one inside the balloon, is 1.2 kilogram meters to minus 3. Notice that the air inside the balloon is less dense. That makes sense, right, in your heads? That the air in the balloon would be less dense than the air inside on the outside, and therefore would hop it goes. And then we just plug those into this equation up here, right? So we just plug that into there. They go into there. Off they go. Woo! Look at them go. And that gives us R equals. It's 21 or 6. 5.5. It's 5.71, which when we double that, because we want the diameter, we get F27.1, we get 11.42. And that's the answer. Okay? It's a big old balloon.